Welcome back. Last week we talked about some basic kinematics and derivatives. This week we're going to talk about using the kinematic equations in one dimension for some rocket problems. Okay, so let's just get right to it. So D1, a model rocket is fired vertically and starts from rest. It ascends with a constant acceleration of 3.5 meters per second squared for 10.0 seconds. After which the fuel is exhausted and the rocket becomes an object in freefall, eventually falling back to Earth. Ignore air resistance. What is the speed of the rocket and what is its height above the ground after 10 seconds? Okay, so essentially with this problem we are given three scenarios. Okay, we have a rocket burning fuel with an acceleration of 3.5 meters per second. 3.5 meters per second squared, excuse me. Okay, for 10 seconds. That's scenario one. We have scenario two, where that fuel burns out, and after 10 seconds, we are no longer left with an acceleration of 3.5 meters per second squared. We are only left with the acceleration of Earth's gravity, negative 9.81 meters per second squared. Okay, we don't know the time. Okay, and then there's going to be a third scenario where the rocket stops moving upwards, briefly hovers for a second, and then comes back down towards the ground, again with standard g as acceleration, negative 9.81 meters per second squared. Okay. I should probably split this into, excuse me, I should probably split this into 4 different sections. 3 is fine, but to make it more explicit, I would like to describe that the rocket is going to be sitting at the top. Here's a rocket. It's just going to be stopped. Velocity is going to instantaneously be 0 at the very top of its flight path. This is also where we have our maximum y value in height. Okay? So the first question says, what is the speed of the rocket and what is its height above the ground after 10 seconds? So pretty much we can just use the standard kinematic equations and plug it in for the first trip, okay? So we have y equals y naught plus v naught times t plus 1/2 acceleration times time squared. Okay, we're told the rocket starts from the ground. We can assume that y naught in this case is 0. We're told that it starts from rest, so initial velocity is going to be 0. So we can find a height by using the acceleration that we're given, 1/2 times 3.5 meters per second squared times 10 seconds squared, right? So that gives us 175 meters. Okay, we'll call this y1 because we're talking about the first trip. Okay, next, D2. We are asked how long, oh no, sorry, we need to know the speed of the rocket as well. So going back to our standard kinematic equation here, if we take the derivative of this equation, we'll end up with a function for velocity. So the constant goes away, it's going to be 0 plus v naught plus at. So v naught of t, or v of t is equal to v naught plus at. We want to know what the speed of the rocket is after 10 seconds. We have an acceleration, we have a time. we know that v naught is 0 because we're starting from rest. So v is equal to 3.5 meters per second squared times 10 seconds is going to equal, excuse me, 35 meters per second. So there we have our answers. So the height is 175 meters. The velocity is 35 meters per second. So this is the answer for D1. Now, D2. How long does it take for the rocket to come to rest at its maximum height? Okay. Well, we have to consider that we're starting from trip 2, right? So we need to solve for the time. We already know that it's traveling for 10 seconds. We need to solve for the time that it's going to take for the rocket to leave trip 1 from 10 seconds and reach a velocity of 0 at the top, right? So that's going to give us, so we have v is equal to v naught plus at. We can solve for time using this equation. We know at the top of the trip, the velocity is going to be 0. We also know that starting out, we solved for this last in the last part. Starting out, our velocity is 35 meters per second. Okay, we know also that our acceleration is negative 9.81 meters per second squared, and we don't know time. So pretty much we have 35 over 9.81. This is equal to time, and this is going to be 3.5677 seconds, okay? Or in units, I should show our units explicitly. We had meters per second over meters per second squared. So that means that these cancel, one of these cancels, and this goes on top, leaving us with seconds. So answer is going to be so we want to add the time. So how much time does it take for the rocket to come to rest at its maximum height? I'm assuming that means from the start of the trip, the very beginning of the trip. So we're going to add the first time, which was 10 seconds, plus the second time, which was 3.5677 seconds. And that's going to give us, let's just write this out first. That's going to give us 13.5677 seconds, where if we do a reasonable amount of rounding, it's approximately 13.6 seconds. So that is the answer. And that could be due to my interpretation. If it's just asking for how long does it take from trip 1, from the end of trip 1 to the top of its path, that's just 3.5 seconds. But I'm assuming it wants the time for the whole trip, okay? Now we need to solve for maximum height. Okay. So let's do this. First, we need a general form for the time. So D3, we want to find y max. Okay, we can use, so we want the time that it's going to take for velocity to equal 0, right? The overall velocity to equal 0. So that's going to be 0 equals v naught plus at, okay? Which means that the time it takes to get to that point is going to be negative v naught over a. All right? I think I'm going to go ahead and, just so I can show the general form of this, I'm going to actually keep velocity not equal to 0. So then what we're going to say here then is that, okay, so starting from here again, v equals v naught plus at. We're going to go v minus v naught over a equals t. So this is the time it's going to take to reach y max. Okay, so then we can plug that in. So we can say y max is equal to y naught plus v naught times the time, which is v minus v naught over a, plus 1/2 a, and then we have time squared, so that's v minus v naught over a squared. Okay, that's going to give us y naught plus v naught v over a minus v naught squared over a plus 1/2 is a squared, 1 over 2a, v squared plus v naught squared minus 2v v naught. Right? Simplifying this a little bit, we're going to end up with y naught. Let's see, what do we have here? So we got, let's just group all of our like terms. Let's make things a little easier. V naught v over a minus 2v naught v over a, right? So that's this term and this term minus, sorry, those go away. Where was I? This term, this term. I'm just going to write all this out, right? So we had 1, 2, 3, 4, 5 terms, 1, 2, 3. So I only had 5. What I'm missing something. Minus v naught squared over a. That's what it is. All right. So now we have y naught plus. These terms go away. Then we're just left with these other two terms. Over 2a plus this 1/2, right? So then we just have plus v naught squared over 2a. So this is equal to y naught plus v squared minus, this is actually should be negative, excuse me, minus, right? I see, I made a mistake here. I wrote down this as negative. This should be positive here. Yep, there we go. Positive minus, okay, there we go. So I just wrote something down wrong. V naught squared over 2a. Okay, so this is y max. Okay? V squared minus v naught squared over 2a. So in our case, we actually have y naught is equal to 0, right? So our y max is equal to v squared minus v naught squared over 2a. But at the maximum height, you're not going to have a velocity. So what we want to say then, let's go back. Oops. Add marker. There we go. Okay. So what I'm saying is that we want to add these two things. So we have two trips, right? We have y1 max and we have y2 max. And that's going to give us our total height. Okay? So for trip 1, we already know we traveled 175 meters. So that's 175 plus y2 max. Okay? So now we plug in our values for the velocity at the top of the trip, which is 0, and then we also have our initial velocity, which was 35 meters per second for this trip. This is trip 2, remember. So we have 175 plus. Let's just write it all out so we can see. So 0 minus 35 meters per second. And this is squared, by the way. And then we have over 2 times negative 9.81 meters per second squared. So this is going to give us our value that we're looking for. Okay, so plugging this all in, this gives us 175 meters plus 62.436 meters. This is Y max. Okay, what is that together? That gives us 237.44 meters. So Y max is equal to 237.44 meters. Okay, so just reviewing a little bit. Okay, I need to clarify that this is not entirely necessary to go through all of this. This was just so that you could see it. Here, show you. All of this is not necessary for you to do on a problem. Typically, you're given this information. Y max is a pretty standard equation that you can use in kinematics. I was just showing you how to get there. Okay, so, but the important point is that you're going to need to use two values for y. Because we found the first trip was 175 meters, and then you need to find y max for trip 2. Okay, so that's what's important there. All right, moving on. D4. What is the speed of the rocket at the instant that it hits the Earth? Okay. So to solve this part of the problem, this is our fourth. If we go back up and we look at the diagrams that I drew in the beginning, this is where we are here. Okay, so we know what the acceleration is. We know V naught is going to be equal to 0 because we're starting from rest at the very top of our path, right? So we traveled up, right? We went all the way up here. Instantaneously, there was some rest, and then we started on our trip back down. So here V naught is equal to 0. Okay, we're trying to solve for V, so V is equal to V naught plus AT, right? We want the time. We're going to need the time it takes to fall back down, and we're going to need the speed. All right, so let's find those things. So, as in most kinematic problems, we can use the kinematic equations that we know. We have, recall, y equals y naught plus v naught t plus half at squared. Okay, so we need the time. We know actually quite a bit of this information. If we simply set, let's say that y is going to be 0 because we've defined our axis to where the ground is 0 meters, right? So then we've got 237. We're starting 237.44 meters up. Okay, V naught is 0, so that can just go away. We're good with that. Negative 9.81 meters per second squared times time squared. Okay, so now what we're left with is negative 237.44 meters over, well, we need to multiply this by 2 because we're solving. I'll be more explicit here. Let's do this so that you can see what I'm doing. So I take this to the other side. Then I multiply this to the other side. So now I have 2 times negative 237.44 meters. Okay. Now I'm going to have negative 9.81 meters per second squared is equal to t squared. We're solving for t, right? And look, these negatives will cancel. So now we're left with t is equal to 2 times 237.44 meters over 9.81 meters per second squared, all under a square root, right? This gives us, final answer, time is equal to 2.6 2.6377 seconds. So that's the time that it's going to take for this rocket to fall back to Earth. Okay. The tricky part for me, at least in figuring these out, is just identifying what your starting points are for each trip. Okay. So that's, if we go back and we just kind of briefly look at this again, remember that we defined y is 0. That's our final destination. Our starting point was up 237 meters, right? Initial velocity for this trip down to Earth was 0. We started from 0. And then we know acceleration is due to gravity, and then we solve for time. Okay, so this is what we get. So now what we can do is we can plug this time into another kinematic equation. Recall that velocity is equal to initial velocity plus acceleration times time. And pretty much we just plug in because we have, okay, velocity is going to equal, we have 0 plus negative 9.81 meters per second squared times what we just found, 2.6377 seconds, which is going to leave us with units of meters per second. So this is going to be negative 25.87 meters per second. 25.87 meters per second. And it's negative because we're going in the downward direction. So we could just say this is y hat, right? So if this is our velocity vector, that's what we're looking at. So really, if we're just looking for the value, the scalar value, it's 28.87 meters per second. That's the answer. One thing that's a quick bonus that you could use, sometimes you're asked to find the total time for a round trip. Let's see if this. Okay, so if you're asked to find the total time it takes for the round trip, you simply add our times. So we had this time here, 2.377 seconds. Of course, you can round and use significant digits. I'm just keeping everything the way I find it. Let's see, what was the other time? We had it up here somewheres. Okay, here it is. Just take this, copy, and then we paste it here. So we add those two things together. This is T2 plus T1, right? That's going to be total time, T net. And that gives you total time for the round trip, 16.21 seconds. That's rounded a little bit. There we go. You're not asked this in the worksheet, but it's very likely you'll be asked this in another problem. Okay? Cool. Good. I think I have covered everything in the rocket problem. Just checking my work real quick. So remember, the best strategy to approaching these problems is to identify that there is more than one trip, right? Because we were told that we had an acceleration for 10 seconds. That's trip one. Once that 10 seconds is up, our acceleration changes. Okay. And we also had that velocity was 0 at the top of the path when we found y max. That's really important to remember. And then you have another trip on the way down, right? So trip 1 was the first 10 seconds. Trip 2 was after that 10 seconds, acceleration just changed to negative 9.81 meters per second squared and went to the top where velocity reaches 0, right? So to give you a better idea of what I'm talking about, I'll just draw it out again. Just to be clear. So this is the first trip, right? Acceleration was 3.5 meters per second squared. The time was 10 seconds. Then we had another trip, which actually, I guess if I'm drawing it, trying to be accurate, it would start from this height, right? So this was 10 seconds. This ended up being around 3.5 seconds, about. Okay. Then the rocket just kind of stays here, hovering briefly, just for a moment, okay? So v is equal to 0 at this point. At this point, we found this, right? So at this point, this is negative 9.81 meters per second squared because our boosters turned off. Our rocket boosters turned off, and now we're left with just the acceleration of Earth's gravity due to Earth's gravity. Okay, so these were the first two trips, first three, I guess, if you want to consider it that way. And then we had here, the fourth trip was traveling back down, right? Initial velocity in this trip is 0. Acceleration is equal to 9.81 meters per second squared. We know the height. We were told because we found y max, right? So this is where you would find y max here. Y2 max was found here. And then you add that plus y1 gives you y max. Okay? So you can plug all of this into the last trip to find your final velocity. Okay, this is just a quick recap in case any of the steps I went through was a little bit too fast or confusing. Feel free to always email me too, and I'll try to explain it more clear if I can. Okay, next question. How are we doing on time? Pretty good. We only have we're only 26 minutes into the discussion. I think we'll end even a little bit early today. So let's see what we got. Okay. So next question, D5. In this question, you will take a look at resisted motion. Start by considering a velocity that varies as v equals v naught over b times t plus 1. V naught is a constant, b is a constant, 1 is a constant. So the first part asks, is the particle slowing down or speeding up? Okay, well, let's just write down our function here real quick. So if we were to take this function, we could graph it, but without even really needing to do that, let's break this down a little bit. So we actually have a constant on top. We have a variable on the bottom multiplied by a constant and added to a constant. So let's just rewrite this just for clarity, and we'll say that this bottom portion here, this down here is just, we'll call this a variable function, right? We'll say that this is some function alpha. So now we have v of alpha. So now we know that v is proportional to 1 over alpha. So as alpha increases, v is going to decrease. So that means that v is slowing down. That's what I'm going to say. And so we can actually check this by taking the differential of our velocity and seeing what we get. So let's try that. V is equal to v naught over bt plus 1. We want to find dv dt. That's going to equal, remember we just have a constant here, it's going to equal negative 1 times bt plus 1 all squared times dt dt. That's just equal to 1. So really we're left with negative v naught over bt plus 1 all squared. So the acceleration is decreasing. So velocity is changing in the negative direction, right? So acceleration is going downwards. Okay? So that's just what we expected by looking at this sort of qualitatively on the top. All right. This might be, maybe how I wrote that was a little confusing. We'll just call it. All right, so next part. Challenge. By integrating this expression, find an expression for the position of the particle at some time t. Okay. Discuss with your TA whether the particle ever comes to rest. Well, I'm the TA, so I'll discuss it. This is a subtle question and will involve considering the limit as t goes to infinity of x of t. All right, so the first thing we need to do is do the integral. Okay, let's do that. call that velocity is dx dt. We want to find the position, an expression of the position with respect to time. So what we need is to integrate v with respect to t, right? So that's going to give us some function of time. Let's do it this way. I don't need to rewrite it. Let's just move on. Okay. Now, so x is going to equal the integral. Let's say we're integrating from 0 to some time. Okay. V naught over b t prime. We'll call it prime because we already have a t here. We don't want to get confused. So let's just call this variable prime. dt prime. All right, so the easiest way to do this integral, in my opinion, is to do a u substitution. So let's do a substitution for the function in the bottom. U is equal to bt plus 1. That means that du is equal to b dt. That means that 1 over b du is equal to dt. That's useful information. And then we want to say that we're from 0 to t, so that means that u is going to be from 1 bt plus 1. That's not right. Hang on. Oh, no, that is right. It goes, because we're just inputting t as t, right? T is t prime. So anyway, I'll just write it out. Really, I should have had all of these as primes. So this is what we're looking at. Now our integral has been transformed, right? So we have 1 to bt plus 1 of v naught over b times 1 over u. Let's just say this here. We'll just write it out. 1 over u du. Okay, this is our integral. Let's come down here. Okay, so this is what we're left with. We can move this, put these over here. These are just constants out front. Well, what is the integral of 1 over u? That's something that we all know, right? It's going to be the natural logarithm of u. So now we're left with v naught over b, natural logarithm of u from bt plus 1 to 1, which gives us v naught over b. Let's just box this in. So now we have ln bt plus 1 minus ln of 1. Okay, well, that's kind of fortunate because if we look at this, we can actually see ln of 1 is always going to be 0. We actually have, if we just graph ln real quick, we see it's something like this. Let's call this 1, right? This is position 1. This is t. This is y of t, some function. Oh, x of t, excuse me, x of t. Okay, so we go here like that. What I'm trying to show is that this crosses at 1. X goes to 0 as t goes to 1, okay? So that's nice that we can get rid of one of these terms. So now we're left with x of t is equal to v naught over b ln bt plus 1. Cool. Well, so this is sort of a weird function to look at and try and determine what's going to happen. So now maybe we could try taking the limits because that is what is suggested, okay? So let's take the limit as t goes to infinity. All right, well, the limit as t goes to infinity of x of t is equal to v naught over b. Well, as t goes to infinity, we're just going to get the log of infinity. And if we look at this graph I just drew over here of the natural log, let's call this ln t. trying to change the color. There we go. So if we look at this graph of ln of t, as t goes to infinity, this function just keeps going towards infinity. It just keeps going, right? So it doesn't go to 0. It doesn't disappear. So then what does that really mean? So it tells us that the particle is going to continue forever. But we know that that's not true because we know that we're not just going to have a continuous function that just goes forever, right? Like for position. It's not just going to keep going, because what happened was earlier we found that here, the velocity, we found this to be decreasing, right? As time increases, velocity decreases. We also showed this here by taking the derivative and showing acceleration. Acceleration is going in a negative direction. That means it's resisting our motion. So this is resisted motion. Okay, so we know that at some point, if we just continue with a constant velocity as we are, I mean, if we still have v naught and we still have this acceleration, that's really what I'm trying to say. We are going to come to a stop. So what does this really mean? Let's write this out again real quick. So v is proportional to 1 over t. Acceleration was proportional to negative 1 over t squared, right? This indicates decreasing velocity. This indicates negative acceleration. Okay, and if we consider we had for kinematics, right? We have these equations of motion, but these only work for constant acceleration. So now if we look over here at if we're looking at this function of acceleration, this is not a constant. It depends on t. So these kinematic equations won't work anymore, right? So really, I guess the main point here is that, yeah, we found this function to tell us that the position would just continue forever with time, but the subtle aspect of this is when we look at the velocity and the acceleration, we actually get a lot more information from it, okay? So the final conclusion, I would say, if the propeller stops working, the particle is definitely going to come to rest. So you have to have something that defeats this resisted motion, right? So here is your resisted acceleration, your negative acceleration from resisted motion, because we're moving through some fluid, right? It's like what is it, a submarine? Well, that's what I assumed because of the way the function looks. So I would assume it's something moving through a fluid, and thus the motion is resisted. And so in order to overcome that, you need to have some acceleration that can defeat the negative acceleration that we found here, right? So it will come to rest. That's final conclusion. All right, I'll write it down. And see you next time.